So we can go ahead and get started. Welcome to our webinar, Transforming the Global Power Sector, Open Tools and Data for Renewable Energy Integration. This webinar is brought to you by the Global Power System Transformation Consortium and the USAID-NREL Partnership. Before we get started today, here are a few housekeeping rules. This webinar is being recorded and will be shared with attendees after it's finished. You are automatically muted upon joining and throughout the webinar, but you can use the Q&A function at the bottom of your toolbar to ask questions, which will be addressed during the Q&A portion at the end of the webinar. Please use the chat feature, as you are doing now, to introduce yourself and add comments and share input. If you have any technical issues, please use the chat feature to message my colleague, Isabel McCann, or message me, Holly Darrow. You can adjust your audio through the audio settings. If you are having issues, you can also dial in and listen by phone, and this information can be found in your registration confirmation email. Today's webinar also offers a side-by-side learning code package. To view that package, please visit the link on your screen, or my colleague Isabel will put it in the chat. So to go over what we're going to cover today, my name is Holly Darrow. I'm a communications strategist at the National Renewable Energy Laboratory, or NREL, and we're going to hear from some amazing presenters, including Karin Wadsack. Karin is a program manager for NREL, where she directs the Global Power System Transformation Consortium and performs applied energy analysis for energy system decarbonization and resilience projects around the world. She has more than 15 years of experience in energy analysis, policy, and project development. Her background also includes business management, international development, and work with Native American tribes across the United States. Karin holds a PhD in engineering sustainable systems, a certificate in applied statistics, a master's degree in environmental science and policy and journalism, and a bachelor's degree in government. We're also going to hear from Dr. Galen Maclaurin, who is a senior energy researcher and manager of the Geospatial Data Science Group at NREL. He leads the development of mesoscale wind and solar resource data sets at the intersection of atmospheric science, machine learning, and big data processing. He manages a geospatial modeling team that develops scalable, innovative methods for understanding the barriers and opportunities for future renewable energy deployment from a cost performance perspective. And finally, we're going to hear from Dr. Kate Doubleday, who is a model engineer and researcher in NREL's Grid Planning and Analysis Center. She has a PhD in electrical engineering and research experience in power systems, operations, renewable energy forecasting, and vehicle electrification. Today, our wonderful speakers are going to cover our opening remarks by Karin. They're going to go through the RE Data Explorer, the Renewable Energy Data Explorer, a tool for high-quality data for decisions. Then moving on to enabling power sector transformation at scale, introduction to production cost modeling, or PCM, open source tools for PCM development, and finally, an overview of sample analysis and training materials. And then to briefly touch on what we're going to cover tomorrow, we'll do a short recap of today, an overview of PCM workflow, resource visualization and site screening using the RE Data Explorer tool, PCM demonstration in the Sienna Ops tool, open source training resources, Q&A, and a wrap-up. So that is our overview. And with that, I'm going to hand it over to Karin Wadsack to go over our opening remarks.
Excellent. Thanks so much, Holly. So as Holly mentioned, my name is Karin Wadsack, and I have the pleasure of serving as the director of the Global Power System Transformation Consortium. So I'll start off with a brief overview of the Gpst and the USAID-NREL Partnership, and then I'll explain a little bit about the purpose of today's and tomorrow's events. Gpst was formed by 6 system operators in countries that are among the farthest along in the world in decarbonizing their electrical systems. And the goal of G-PST is to develop technical solutions and share those worldwide in order to advance progress on climate change and to support the global energy transition. And this consortium is focused really closely on the needs of power system operators and works via a number of different modes in order to develop, deliver, and scale the needed technical solutions worldwide. Next slide. The 5 different modes of operation for G-PST are shown here. And the first of those is cutting edge system operator research and peer learning. And that's led by the Energy Systems Integration Group in the United States. And the activities here include research, technology, piloting and demonstration and deployment, and then a lot of peer learning and shared knowledge across the audience of not just system operators, but other technically interested parties such as industry, academia, developers, software engineers, et cetera. The second area of G-PST is system operator technical assistance, and that is led by the National Renewable Energy Laboratory. And that includes direct technical assistance projects between system operators in different countries, as well as specific data applications like we're hearing about today, and deployment of different kinds of tools and techniques. The third area of activity is workforce development, and that is led by Imperial College of London. And that includes the identification and development of key curriculum areas that are gaps between current electrical engineering graduate education and what system operators may need when they're actually on the power control room center and power plant floor. And that those curriculum we've been emphasizing a lot of curriculum development by female engineers, and that is something that we're really proud of. Another couple areas under workforce development include fellowships between system operators, where participants have the opportunity to work on projects together and share knowledge, learn from each other, and then internships at different technical institutions within the G-PST core team. The fourth area is localized technology adoption support, and that is led by the IEEE in the United States with collaboration from IEC and other standards associations. And the goal there is to identify and develop standards that will be needed as we consider the changes in the electrical system during the energy transition, and then to work in appropriate contexts in different countries around the world to implement standards. And the last area is open tools and data, and that is really part of the center of this event today and tomorrow. This is led by VTT and also has strong participation by NREL. And the work in this area is to identify available open source tools and data structures, and then also to work to identify gaps and work on the development of additional tools in power system planning and power system operation, in order to have a set of tools that ideally would, at the end of the day, be interoperable and run the gamut for all of the different needs in the workflows of power system operators. And in addition to that, of course, there's very strong importance of open data and data structures, and we'll be hearing a lot about some of the different opportunities there today. Next slide. G-PST and the USAID-NREL Partnership work very closely together on power sector programming and on special initiatives like today's and tomorrow's learning sessions on open source data and tools. And so for anybody who isn't already familiar with it, the USAID-NREL Partnership collaborates with partners around the world to advance critical aspects of energy system modernization and the clean energy transformation. Work across this partnership spans the power, buildings, and transportation sectors, providing technical tools and targeted decision support that can advance integrated and cross-sector clean energy solutions. Next slide. One of the key ways that the USAID-NREL Partnership supports knowledge sharing and good practices on clean energy transition topics is through our 4 global knowledge platforms that are shown here: the Renewable Energy Data Explorer, the International Jobs and Economic Development Impacts Model, Greening the Grid, and the Resilient Energy Platform. These platforms collectively provide publicly available technical knowledge resources and tools to support energy sector stakeholders around the world with diverse aspects of clean energy decision-making. Next slide. So I'd like to briefly highlight 2 of those platforms for the purpose of today's webinar: the RA Data Explorer and Greening the Grid. RA Data Explorer is a user-friendly web platform and open data download repository. It enables users around the world to easily access renewable energy resource data and analytics, meeting a global need for improved public access to high-quality renewable energy data for decisions. This platform can support renewable energy resource mapping and visualization, early-stage prospecting, and technical potential analyses, to inform decision-making about renewable energy projects, planning, and policy. Importantly, Renewable Energy Data Explorer also enables users to download at no cost high-fidelity solar and wind resource data sets for many parts of the world that can be used to support power sector planning and the integration of renewable energy technologies onto the grid. Similarly, the Green in the Grid platform as a whole, and specifically the Grid Integration Toolkit, offer cutting-edge technical information, best practice frameworks, and training resources to support a range of energy sector stakeholders at different stages of power sector transformation and grid decarbonization. Next slide. One of the key points that I wanted to highlight to kick off today's webinar is the importance of open data and tools such as those provided by G-PST and the USAID-NREL Partnership to transform global power sectors and support effective integration of high shares of renewable energy. We're really excited to share today's and tomorrow's sessions with all of you because expanding public access to high quality data and open source tools for power sector decision-making can truly catalyze innovation and development of novel solutions, accelerate clean energy deployment and investments globally, and empower decision makers at all scales to plan for and achieve their clean energy transition goals. We hope you find these resources and tools useful and that you can share them with others who might benefit from them as well. And with that, I'd like to thank you for your time and your participation today and tomorrow. And I'm going to hand things off to my colleague, Galen Maclaurin, to kick us off with today's technical content. Thank you very much.
Thanks, Karin. Great. Welcome, everybody. Thank you for joining us today. I'm Galen Maclaurin from the National Renewable Energy Laboratory, and today I'm going to walk you through public open access data that NREL has been providing, growing project across the globe with a focus on wind and solar data today. So to start, just to position this part of the webinar, high fidelity resource data is really the foundation for modeling, for site evaluation, for long-term energy planning. And so particularly relevant for the topics in this webinar, having very high spatial and temporal resolution wind and solar data is crucial for understanding what future scenarios would look like in operating a grid with large amounts of wind and solar, and what that means with the existing fleet of generators on the system. And so being able to capture with high fidelity, the high variability of these resources. So I'm going to touch just a little bit on some of these, and then my colleague Kate is really going to go into a lot of depth on how these data are used in some of the tools that NREL provides in power system modeling. So the motivation and the objectives for this project. First, we really wanted to democratize these data. So high fidelity wind and solar resource data have traditionally been commercial products that had to be purchased that were very expensive, especially when you wanted to do analysis across broad geographic extents. And so really that was kind of the principal motivation for developing these data sets. These data sets support everything from project feasibility assessments, regional and national target setting, detailed power system modeling, which is the focus today, and also really important understanding the complementarity between PV and wind. To be able to understand that, you need to have high fidelity, both wind and solar data. And so the objective here, very simple, is to provide the highest quality data that we can produce, make it publicly available, make it easy to access for the public. And so the value proposition here is really focused on the energy communities. So trying to capture with the highest fidelity we can atmospheric processes that are important for modeling wind energy, for doing site evaluation for wind projects, and understanding the important components of the atmosphere that interact with solar radiation, and representing both of those in data sets that capture with the highest accuracy possible mesoscale wind flow and solar irradiance. Really important is that we're able to capture the sub-hourly all the way up to interannual resource variability. So this, as these are both very highly variable resources, to understand how these resources change from minute to minute, sub-hourly, all the way up to understanding that variability across decades. As we know, wind and solar can vary depending on the site you're at, up to 10 even more percent per year. And then particularly relevant for power system modeling is being able to capture those ramping rates. So this is, rapid increases or decreases in the solar resource, and thus the generation from a wind plant or from a PV plant, and how the power system can deal with that, and understanding that, be able to represent that in a model. And so that's another really important component that we focused on, is capturing those ramping rates the best that we can at fine temporal scales. And then specifically just for wind resource, being able to accurately capture the vertical wind profile was referred to as wind shear. And we know that turbines are just going to get larger and taller to access that better resource at higher heights above the ground. So really being able to capture that as accurately as we can. What is the benefit of going, say, from a 100-meter turbine to 120 to 140 to even 160-meter turbine, as we see the future direction of the industry going? Okay, so I'm going to start with solar, and then I'll walk through wind next. So this project is now global at NREL. We started with the Western Hemisphere, covering the Americas. We now have global coverage, nearly global coverage. It goes as far as 6 degrees north and south latitudes. I'm going to focus today on the data set we produced for Southeast Asia, but just to mention, we have 24 years of solar resource data for the Americas. We have 3 years available for Africa, Central Asia. We're currently producing a new data set that will provide a longer term record for that area. We have an older data set that is still great for a lot of power system applications that covers South Asia, a 14-year data set that covers India. So this is a growing project. We continue to update these data sets every year. I'm going to walk you through at a high level and of what the algorithm is and how we produce these data. So the model that we use is called the physical solar model, NREL's PSM. What this model does is it characterizes the absorption and scattering of the solar radiation as it travels from the sun through the atmosphere, interacts with the atmosphere, interacts with the surface, and ultimately estimate how much solar radiation is available at the surface for solar energy generation. So the two most important components in this are clouds and aerosols. So I'm going to talk a little bit more in depth on clouds. So I'll start with aerosols. Aerosols are particulates, small particulates in the atmosphere that absorb and scatter that solar radiation. So examples are ash from volcanic eruptions, dust, contamination from cities, pollution, carbon in the atmosphere. So these are small particulates that will change the direction and the intensity of that solar radiation as it's passing through the atmosphere. We also model with very high detail other atmospheric constituents, so trace gases such as carbon dioxide, ozone, and water vapor. These atmospheric constituents also have an impact on the amount of solar radiation that will make it to the surface. We also model the land surface. So the surface reflects the solar radiation, which then goes back up in the atmosphere and interacts with the other constituents that I've talked about, the other components, and can reflect back down to the surface. It's also important for the emerging bifacial panels. So for example, in a desert environment, you're going to have a much higher reflectivity of that surface than in a dense vegetated area. And so that's called albedo, and we represent that in the model as well. As I mentioned, clouds are the most important component of the atmosphere for us to model to accurately estimate the solar radiation. So we partner with a team at the University of Wisconsin, and this is a physical model, which means that it is using satellite imagery. So we use geostationary weather satellites from a number of different systems around the world. You're looking at this image here. This is from the Himawari satellite system. This is from the Japanese Meteorological Agency. And what you're looking at here is the cloud optical thickness. This is essentially how dense and how thick those clouds are, so that we can model what impact that's going to have on the solar radiation. So this is really important, characterizing the type of cloud, the optical thickness, and other properties, so that in our radiative transfer model, we can represent how much that's going to impact the solar radiation. So this is a spatial temporal model that is a grid across the extent, and it has different temporal resolutions where an image is captured by the satellite, and then we model at that time step the total solar radiation that will reach the surface. This data set is validated with a global network of measurement stations. This is specifically the Southeast Asia Himawari data set that I mentioned. I'm going to be focusing on mostly the Southeast Asia data sets today. We use 9 solar radiation measurement stations from a global network. So the average annual mean bias error is typically less than 5% for this data set. As you start to go to finer temporal resolutions, you start to see larger amounts of mean biased error, which would be expected. But at the annual level, which is very important, we're considering a lot of what is the potential of a plant, the annual technical potential, or what is your levelized cost of energy. The MBE is typically less than 5% for our data sets across the globe. This is, get the animation to play here. This is the result of our Southeast Asia solar resource data set. You can see here how we've modeled the clouds, and below, we pull that back, you can see the solar radiation below. This is a 10-year data set. It has 2 different resolutions. The resolutions of these data sets are based on the resolution of the satellites. We also produce a TMY. Kate is going to talk a little bit about what that means tomorrow, but just to mention, we do make that available as well for all of our data sets that have 10 years or more of data, which is required to produce that TMY. Okay, shifting to wind data. So wind is a very different animal. We have to use very different methods to model the wind resource. You can't see the wind from a satellite. So typically what has been used is numerical weather prediction, a class of modeling where the most dominant model and most common model is called the WRF model, the Weather Research and Forecasting Model. This is considered best in class. It's really an amazing model. It's a multidimensional model that represents all of the important components of the atmosphere and how they impact wind flow. It also is a model that represents other components of the atmosphere, temperature and pressure, relative humidity. All these components that really drive kind of storms, and for us in particular, all of that impacts the wind resource. So this is much more computationally intensive than our solar resource, and so we're still working to cover the globe. Just to give you a snapshot of kind of where we are across Asia, at least. We produced 1 year of data for Central Asia. We produced 1 year of data for South Asia, including India, using the WRF model. And we did this for a lot of power system modeling applications. And it's very, like I mentioned, it's very computationally intensive. So in the last 2 years, we've developed a new method, a hybrid approach that brings together numerical weather prediction modeling with machine learning to be able to increase the efficiency and be able to produce longer data sets and cover more of the globe. So I'm going to talk a little bit about this new methodology. This is really changing the paradigm for how wind resource assessment is done. And like I mentioned, bringing together these cutting edge techniques between numerical weather prediction and machine learning. So in particular, what we did is we developed a hybrid approach that uses the WRF model, like I mentioned, kind of the gold standard, the best in class model. And so we use that model to increase the resolution of the data set that we start with. That's essentially what you're doing in wind resource modeling is what's called downscaling. So you're increasing the spatial and temporal resolution from a coarse global data set. So we do that with WRF to a point that the model's still computationally efficient enough for us to run. And then we bring in a machine learning model called generative adversarial networks, or GANs, which is an emerging technique that's really good at replicating physical processes that are important for the modeling application. And so what this allows us to do is produce a long-term data set much more efficiently than we were able to do before. Let me just walk you through the algorithm at a very high level. So we start with a global weather model, what's called a reanalysis data set. This is ERA 5 from the European Union. It's a coarse resolution model in space and time, but it's very good at capturing the global atmospheric processes that drive wind, the wind resource. Then we use the WRF model, and we downscale this iteratively from 30 kilometers down to 9 kilometers. This is still at hourly temporal resolution. So like I mentioned, the WRF model is really good at capturing these mesoscale processes that drive the wind resource. It includes terrain, sea surface temperature, and land cover data sets. So at 9 kilometers, that's where the model starts to get really computationally expensive. So that's when we bring in the GANs modeling. And so what this allows us to do is very efficiently kind of go that last step. And so we downscale using this model from the 9 kilometer WRF data down to our final 3 kilometer spatial resolution, and from hourly temporal resolution down to 15-minute temporal resolution. And so what this allows us to do is create a 15-year data set at multiple hub heights above the ground, including not just wind speed, but wind direction, also the surface temperature and atmospheric pressure as well, which are important and necessary variables for modeling wind turbine performance. This data set is validated with meteorological towers. Just a couple examples, we used 6, but I'm just going to show you 2 real quick. The mean bias error on the far left here, the blue lines, this is at multiple heights above the surface on the meteorological tower. Our bias is centered around 0, which is what we want to see. Our mean squared error, the orange bars, is between 1.5 and 2 meters per second. So these error metrics are in line with what we see from WRF modeling. So this was really our goal, was to increase efficiency without sacrificing accuracy. And then on the right, we have 2 plots here of the diurnal profile, where the model is in blue and the measurement data is in red. And so as you can see, the model data set does a good job of capturing those diurnal patterns. Here's the final output of this Southeast Asia data set. I give you an example here. This was a devastating Typhoon Rai that hit the Philippines. To show it's important for us to be able to capture these extreme weather events so that we can better prepare for them in the future and understand the impact that they will have on our power systems and develop them in a more resilient manner. Also, I just want you to notice how it captures some of these processes across terrain. You see mountain ridges across the different countries in Southeast Asia, where the wind resource accelerates as it moves up across those ranges. Also, some of the coastal patterns as the wind resource interacts with the coast as it goes across the smooth surface of the ocean and then hits the coast. So these processes are captured very well, and hopefully this animation gives you a sense of what this data set looks like. I like to show these because this is not a map. This is an animation. This is a spatial temporal data set. Okay, so how do you access these data? To wrap up here, as I hand it off to Kate, we provide multiple options to download these data. We're going to be talking a lot about the Renewable Energy Data Explorer. This is a point-and-click way to access these data. You can go in, you can access all of the solar and wind data for Southeast Asia that I've talked through today. We also provide 2 options for programming interfaces, traditional API, where you can access larger amounts of data. You can do it in an automated way using different programming languages, such as Python, which is probably the most common, but also other programming languages. We also have another service called the Highly Scalable Data Service, HSDS, that gives you a different way to interact with the data, essentially just a different type of API, but it's particularly nice if you're working in Python and you can pull down the data as Python objects and interact with them in different ways. Both of these, actually all 3 of these examples are very easy to integrate with other NREL tools such as SAM, which Kate, my colleague, is going to talk through as well. So I invite you all to go to the RE Data Explorer and take a look at the download options. Kate is also going to walk through an example of that tomorrow. So I will wrap up there. Thank you all and pass it off to Kate.
Thank you, Galen. Let me get my slideshow started. Good morning, afternoon, and evening, everyone. All right, so hopefully folks can see my screen now. I will be presenting first on the general topic of variable renewable energy grid integration. before we talk more specifically about production cost modeling, and then introduce two of the tools that we'll be using in the demonstration tomorrow. So as we look towards using higher and higher proportions of VRE, variable renewable energy, in the power grid, there are some common challenges that folks refer to. So these resources, like wind and solar, have different operating characteristics compared to conventional thermal resources. So these resources are variable and uncertain due to their dependency on the weather. They're also not dispatchable, which means they can't be asked to produce a certain level of power at a certain time. And they also don't provide inertia, which is protective against disturbances to the power grid. So as we look towards using higher and higher proportions of VRE, we need to come up with some new approaches to either mitigate or complement these operating characteristics so that we can mitigate risks while also maximizing the value that we get from renewable resources. Compounding this challenge is the fact that many of the simulation and decision-making tools that have historically been available were designed with conventional thermal generators in mind. So here we're referencing Walter Short, who was an early NREL pioneer in grid integration. And he noted that the existing models do not allow for a detailed treatment of the more important issues for wind and other VRE technologies. And so this has motivated the development of some of the open source tools that we'll be looking at today that were developed with VRE in mind to allow for a high resolution, detailed modeling that can enable more accurate grid integration studies. So what is grid integration? Grid integration is a system-wide practice to enable the efficient use of VRE while still maintaining grid reliability and stability. This can include a range of approaches, including better data collection, as well as better information, new policies that support VRE utilization, and on a more technical approach, grid integration studies can be used to use a series of decision-making tools to help support better VRE utilization. So a grid integration study can include multiple steps, including a capacity expansion model, production cost modeling, and power flow modeling. And we'll talk a little bit more about production cost modeling in a few minutes. If you're interested in learning more about this topic of grid integration, we encourage you to access the Greening the Grid Toolkit, which is a repository of online resources about the topic of VRE integration and includes a guidebook for practitioners. So these links will be available when the slides go out and probably also be linked in the chat. So as we think about VRE grid integration, there are 4 key pillars of power system reliability that are useful to keep in mind. And these pillars of reliability span different time horizons and geographic resolutions. So the first pillar is capacity. Capacity is asking the question, in 5 or 10 or 20 years, am I going to have enough power generation and transmission capacity to meet my forecasted peak load? The second pillar is flexibility. This is asking the question, does the power system have enough flexibility to address that uncertainty and variability, both in VRE, but also in the demand? The third pillar is frequency. So this is asking whether the system is robust to unexpected contingencies or disturbances. And the fourth pillar is voltage. And so this is asking whether the system is keeping voltage within an acceptable range, because deviations outside that range can cause cascading issues, including in the worst case, blackouts. So as we look across these 4 pillars, we are looking over sort of a system-wide perspective and long-term horizon on the left as we look at capacity. And on the right, we're looking sort of short-term local resolution when we look at voltage. So the focus of production cost modeling is really on the second pillar, flexibility, with a little about capacity on the left and frequency on the right. And so that's what we're going to keep in mind as we look towards production cost modeling. As we think about variable renewable energy grid integration, it's important to keep in mind that the timescales for decision-making span 15 orders of magnitude. So we're indicating here the AC cycle, which is 50 or 60 hertz, depending on your system standard. At these high frequencies, we're in the realm of what we call dynamics. So this is faster than human decision-making and human responses. And so we rely on automation to protect the power grid in the case of disturbances. On the other end of the spectrum, we have the planning horizon, which could be years or decades in the future. So this is where we're looking at generation planning as well as transmission and distribution planning. In this middle realm, we have the markets. So that can include a capacity market, as well as the day-ahead DA market and the real-time RT market. So the day-ahead market is the realm of the day-ahead unit commitment, where a system operator will decide based on a load and VRE forecast what generation units it wants online to provide energy as well as reserves. Because those are based on forecasts, the real-time market, closer to the real operating moment, is an adjustment for anything unexpected that wasn't captured in the day-ahead market. And so this realm here, including some demand response, the real-time and day-ahead markets, and some medium-term or seasonal hydro scheduling and maintenance scheduling, is the realm of production cost modeling. So this is where we simulate operations for planning. So a system operator will use a production cost model operationally to run its day-ahead and real-time markets. But these simulations can also be used in a planning context to look at different future scenarios based on possible generation and planning and transmission and distribution planning decisions, and simulate how that system would operate in this time frame. So as we think again about those 4 pillars of reliability, there are a variety of different interventions that we could use to increase system flexibility to support higher proportions of VRE. So these interventions include better information and decision-making approaches. So that can include, for example, better renewable energy forecasts. So if we have better forecasts, we can make better day-ahead decisions and support higher proportions of VRE. It could include new types of markets. So for example, allowing VRE to provide ancillary services by holding some margin in reserve. It can include new ways of using our existing hardware assets. So for example, demand response or changing the ramping characteristics of the rest of our thermal fleet. So that might induce some more wear and tear on the thermal fleet with the benefit of enabling more VRE integration. It can also include entirely new hardware. So that could include transmission expansion to build out into new regions where there might be a diversity of resources that haven't been integrated into the system yet. And it can also include storage, which is a classic approach considered in conjunction with VRE, including sort of hybrid solar storage or wind storage plants. So most or all of these flexibility options can be simulated with a production cost model. And so a production cost model can be used to compare and contrast different flexibility options to help with decision-making. So that brings us to our more detailed introduction to production cost modeling. So why a production cost model? These models are useful not just for system operators, but also for developers, policymakers, and researchers to ask a diversity of questions. One benefit of a production cost model is that it can be used to assess the impact of an individual VRE plant on the grid, and also understand the impact of the grid on that plant's operations. So a production cost model can answer questions such as what are the cost and reliability impacts of new policies? If we're looking at developing new VRE plants, what are the most valuable locations to site those developments? We could compare different operational or bidding strategies, particularly when storage is involved. And we can also look at the impacts of transmission. Do we need more transmission to enable the development of resources in a certain region? And or is transmission congestion impacting the value of our current VRE resources through forced curtailment? So we'll talk now about how different users might integrate a production cost model in their workflow, starting with system planners and also policymakers. We're showing here again the VRE grid integration study overview. So a system planner looking into the future might start with some forecast of its future demand, looking next year, 5 years, 20 years from now. Using a capacity expansion model, a system planner can come up with a variety of future generation and transmission scenarios. Each of those scenarios can then be run into a production cost model. So the production cost model gives an estimate of how that scenario will operate over the course of, say, a year. We can use the outputs of the production cost model to understand and identify which periods during the year the system is most stressed and is most vulnerable. And then we can use those time periods for a further deep dive. So using those periods of interest, we can then run a power flow simulation to verify that the system is robust to a variety of contingencies and disturbances. Then these models can also feed back into each other. So if there are key deficiencies identified, we can use those to refine iteratively our capacity expansion decisions and production cost modeling flexibility decisions. So the outputs of this type of planning process can look something like this. This is the India renewable integration study that NREL did, that I believe the results are available on the Greening the Grid website and will also be linked here. So this compared a variety of scenarios, including the 6 shown here, that had different market and flexibility options considered. And so for each of those scenarios, we can identify cost savings, as well as renewable energy utilization or curtailment. So based on this type of scenario comparison, a decision maker can select what option is most in line with their goals. So we've looked thus far at how a system operator might use a production cost model. Now let's look at how a VRE developer might integrate a production cost model in their workflow. We're showing here the project development timeline, starting with an initial idea, which then goes through the concept development stage. The concept development can include 2 studies, a pre-feasibility study, sort of a rough scan to identify possible options, and then a more detailed feasibility study. The best options that come out of the feasibility study then go through business development and project execution. So if we look more at the concept development stage, 2 of the tools that we're talking about today can be useful here. So when we're looking at a pre-feasibility study, where we're scanning through a variety of options to try to identify possible locations for development, the RE Data Explorer can aid in that resource prospecting step to help zoom in on likely locations for development. A production cost model, PCM, can then be used in a more detailed feasibility study for likely locations. So the production cost model can be used to understand the possible impact of operations on that project's feasibility. So that could include comparing, again, different bidding strategies, particularly if the project includes storage. It could understand the impact of transmission congestion on local curtailment, and also identify how the VRE plant will displace local emissions. And all of those might impact the desirability and feasibility of the project. So with that framing in mind, let's dive into the structure of a production cost model. A production cost model is fundamentally an optimization problem. And an optimization problem can be phrased as either trying to maximize or minimize a certain objective subject to realistic constraints. So in this case, a production cost model is typically trying to minimize the operating cost of the system subject to the practical constraints of the generator and electric grid. That word problem can be then written as a series of mathematical equations in a mathematical program such as JUMP, which is written in the Julia language, and that's what we'll be using in the demonstration tomorrow. So the combination of the objective or goal function, as well as the constraint equations, define what type of optimization problem it is. It could be a linear program, a mixed integer linear program, or a more complex problem. Once we have that structure, we can then use either a proprietary or open source solver, and various open source solvers are available to solve the problem and identify the minimum operating cost. So this is what a production cost model might look like. We have a cost function that describes the operating cost of the system. We have a series of constraints, including the generator and branch power flow constraints, as well as constraints due to the transmission system. We can also include constraints that describe the services that the system operator provides, including holding reserves in the case of unexpected disturbances. And we can also describe a series of constraints of how the models feed forward from one time step to the next time step. So this is what the output of this type of production cost model might look like. We might solve over an optimization of 48 hours that includes 24 hours where we're optimizing or minimizing the operating cost of the system, as well as a 24-hour look ahead, which we include to make sure we don't have strange edge effects and we're capturing the sort of the medium-term behavior of some of our slower generators. We step this model forward in 24-hour increments as each day ahead forecast becomes available. Each time we step forward, the new starting state is defined using the ending state from the previous step. So that tells us what generators are on, what generators are off, and how long they've been on or off for. So we can step this type of model through over the course of a year using both the day ahead unit commitment, which we just showed, as well as feeding those commitment decisions forward into a finer time resolution economic dispatch model. So a unit commitment model might be hourly resolution, whereas as we get closer to real time, we might run a finer 5 or 15-minute economic dispatch model. So as you might expect, there are a variety of needs for this type of time varying simulation. We require data about the generators in order to be able to describe both the operating cost of each generator, as well as its operating characteristics and constraints. And those can be unique based on the type of generator that it is. Thermal, hydro, storage, and VRE all have different operating characteristics. We might include data about the system operator's reserve categories, as well as information about the transmission network, including its topology, how it relates to the generator locations, and the constraints of the transmission network itself. And then since this is a time varying simulation, we require several time series data sets. So we, in order to include both wind and solar VRE in our simulation, we need time coincident load, wind, and solar time series. So time coincident means that the time steps are all aligned. So if we're looking at February 2nd, 2018, we have February 2nd, 2018 for load, wind, and solar. And that helps us really capture the impacts of weather on the entirety of the power system. It's also important to note that if we're going to do a two-stage production cost model, like the unit commitment, UC, and economic dispatch ED that we just showed, you actually need 2 time series data sets. So one set for the forecasts for the day ahead unit commitment, and then another set for realizations in real time. That's for the economic dispatch. So since we're focusing today on open source data, we've included a series of links here for some data sets that can be used to meet those data needs for production cost modeling. And this is by no means comprehensive. There are certainly other options out there. But if you're looking for places to get started, these links might be a useful place to start. Okay, so with that, let's talk about 2 of the tools that we'll be using in our example production cost modeling development in the demonstration tomorrow. Galen has already introduced the RE Data Explorer, which will be our source of resource data for wind and solar. And I'm now going to introduce the 2 other tools in our workflow: SAM, the System Advisor Model, which is used as an intermediate step in this workflow, and then Sienna, which is our production cost modeling tool. So this is an overview of our demonstration workflow for tomorrow. We have 3 open source tools: the RE Explorer, SAM, and Sienna Ops. The RE Explorer will be used to do some example early stage resource prospecting to select a few sites to download high fidelity resource data, wind and solar data. So this workflow is a little more similar to how a project developer might use a production cost model rather than a system operator. And that's because we're doing this resource prospecting as opposed to using a capacity expansion model. But the flow would be similar. So we will combine the high resolution resource data for each location with some standard plant specifications and plant loss assumptions for wind and solar plants to model the production of each plant in the System Advisor Model, SAM. So SAM can model the electricity production of a given plant. And by combining that electricity production with some financial information, including cost compensation, financing, and incentives, can give some information about the financial feasibility of that plant. So that includes financial metrics such as the levelized cost of energy, LCOE, the net present value, and the payback period. So this can be useful in that feasibility and pre-feasibility stage of VRE plant development. For the production cost modeling, however, our main interest is in the electricity production profile. So this is a time-varying electricity production profile corresponding to the time-varying resource, wind and solar resource data profile. By combining those electricity generation profiles with other information about the system, including the thermal generator data, the transmission constraints, and the demand, we can run a production cost model in Sienna Ops, which can generate a variety of production cost modeling results, including the hourly locational marginal prices, transmission line flows, generator set points, and renewable energy curtailment. So let's talk a little bit more about these 2 tools, SAM and Sienna Ops. So SAM is a free open source software that can model a variety of technologies in a consistent platform. Through SAM, a user can access high quality performance and economic models that have been developed by NREL, the Sandia National Lab, and other partners. So for each plant, again, you can calculate financial metrics such as LCOE and payback period, as well as perform a variety of parametric and uncertainty analyses. And then these results can be exported in a variety of ways, including CSV and other ways that can make it easy to import into a following model. There's extensive help documentation available, including tutorials and webinars online. So I encourage you to check out the SAM website. SAM has a variety of technologies that you can model. not just wind and solar, but also battery storage, as well as other VRE technologies such as marine energy and tidal systems, fuel cells, geothermal, and biomass. For a given technology, there are then a variety of financial models available. So that could include behind the meter systems, as well as utility scale power purchase agreements, merchant plant financial models, and it also includes a simple LCOE calculator. SAM can be accessed through a variety of ways that increase both in their flexibility as well as their complexity. The simplest way to access SAM, if you're just interested in solar modeling, is through the online PV watts calculator. But if you're looking for the full functionality, including all of the various available technologies, the first place to start is by downloading the SAM GUI. So the GUI is useful for detailed modeling of individual plants. If we're getting towards a large-scale system study, it can also be useful to access SAM programmatically. So there are a few wrappers available to enable you to either develop your own application around SAM, or there's also a Python wrapper called PySAM, which we'll be using in the demonstration tomorrow. So this could be useful if you are trying to simulate many plants with similar specifications. And it can be a little quicker than trying to do that manually one by one through the GUI. Once we get to very large scale modeling, it could be useful to look at REV, the Renewable Energy Potential Model, which is another open source model, which is most useful for very large batch processing and scenario development, and it has the highest learning curve. So tomorrow in the demonstration, we'll be using the second and third options, the GUI and the PySAM wrapper for our case study. So now let's look at Sienna. Sienna is an open source ecosystem for power system modeling, simulation, and optimization. It includes 3 core applications, which have all been developed to support modeling of very large shares of VRE, like wind and solar. So the first application is called Sienna Data, which is built to efficiently intake energy systems input data. And that includes parsing from multiple data formats, including map power, PyPSA, and PSSE. You can also load existing test systems. So if you don't have the full set of example test system data available, there are some test systems already included. This platform can be used to consistently represent millions of devices, including wind and solar, and time series data can be attached to any device parameter. So the production from a VRE plant can be modeled, but you could also include, for example, time varying fuel costs. The next application is called Sienna Ops. So Sienna Ops is the production cost modeling platform. This enables simulation of system scheduling, including those sequential problems we were talking about, including stepping forward day by day through a unit commitment and economic dispatch model. There's additionally a third application, which we won't be talking as much about in this demonstration and webinar, but just to make you aware, this is called Sienna Dyne and allows for simulation of power system dynamic response. So in this platform, you can effectively model both a production cost model and dynamic response on the same set of data. So, oops, wrong direction, sorry. Unlike SAM and the RE Data Explorer, Sienna does not include a GUI. It's accessed programmatically in the Julia programming language. So each of these core applications uses a combination of packages, including some common packages across all 3 applications that you might see in our demonstration tomorrow, including powersystems.jl, powersimulations.jl, and power graphics. So here are some examples of how Sienna Ops has been used in case studies. This is showing a production cost model for a very large system. This is a 2,000 bus system in Texas, the state of Texas in the US, where Sienna Ops was used to compare 2 different scenarios, a base case scenario, as well as a very high solar share scenario, So we can see here the unit commitment results with very high shares of solar in the middle of the day. So again, Sienna Ops can be used for large systems with thousands of nodes and millions of devices. A question folks sometimes ask is, how does Sienna Ops compare to existing proprietary tools? So this is a comparison to the Plexos production cost modeling tool. When we do comparisons on the same data and same system across tools, we do expect there will be slight deviations due to the differences in representation, but we're looking for very good consistency. And we see that here in a comparison on this test system with both a unit commitment and economic dispatch. It's also important to note that while this wasn't done on the same operating system and hardware, we do see that the power systems tool within the Sienna Ops application can solve this problem 2 to 7 times faster than Plexos. And so moving to an open source tool that's been specifically built to model high VRE penetrations doesn't necessarily come with performance costs. In this case, it's much more computationally efficient. A couple other examples of what can be done in the Sienna platform. This is an automatic generation control simulation. So rather than the 2-stage simulation we were looking at with a production cost model that feeds into an economic dispatch, this is a 3-level model, which includes first the hourly resolution day ahead unit commitment, feeding into a 5-minute resolution economic dispatch, then feeding into a 4-second resolution AGC model, in order to verify that the reserve requirements held in the previous model were sufficient. Again, we're not going to be talking too much more about Sienna Dyne, but just to reiterate that this is available. Sienna Dyne includes transient stability simulations to understand the impacts of perturbations and disturbances on the system. Finally, Sienna does include some graphing capabilities. So it includes dispatch stack graphing capability, as well as bar and line chart capabilities. And these can be generated both with a static and interactive backend. So we'll use some of those capabilities in the demonstration tomorrow. If you're interested in learning more about Sienna, there are documentation pages available in each of the Julia packages: Power Systems, Power Simulations, Power Simulation Dynamics, and Power Graphics, which I think will be linked in the chat as well. So these documentation pages include quick start guides and tutorials, which are a great place to start. There's also an active Slack channel that you can join, and questions can be directed to sienna@nrel.gov. So since the focus of today's webinar is on open source tools, we do want to also mention that, of course, these are not the only open source tools out there. There are a variety of other production cost modeling, capacity expansion, load flow, and dynamics tools available for transmission scale modeling, as well as some for distribution scale modeling. So if you're interested in other options, you can Google these and also see the G-PST website here, linked here, for additional information. Okay, so with that, we'll go ahead and wrap up for today and start looking ahead towards the demonstration tomorrow. So to reiterate some of the key takeaways, we talked about these 4 pillars of power system reliability and how the power system flexibility, the second pillar, is key for integrating VRE when we're looking at trying to mitigate and complement the uncertainty and variability of VRE. So these time series production cost modeling can help quantify different options for flexibility and enables us to compare contrast different flexibility options. System operators can use production cost modeling both in an operational and planning context. So operationally, production cost models are used on a daily, hourly, and sub-hourly basis in order to minimize operating costs and also hold sufficient reserve margins. In a planning context, we can use a production cost model to study and anticipate the impacts of different VRE scenarios. Plant developers could use production cost modeling within the site feasibility study context, and that can help anticipate some of the operational impacts on site feasibility. That could include comparing different bidding strategies and looking at impacts of curtailment and local emissions impacts. And so finally, we are providing these open source data and models to try to reduce the cost and difficulty of site pre-feasibility and feasibility studies. And so we hope these are useful to you. As we look towards tomorrow, we'll be looking at a case study system using open source data for Cambodia. So this is based on an open source GitHub repository called PowNet, which has an hourly resolution operational model, including transmission and existing generators. It does not include any wind and solar yet, and so that will be the basis for our little production cost modeling case study demo. So we will use the 3 tools that we looked at today to first identify some likely locations for wind and solar development, to model some hypothetical plants using the system advisor model, and then to integrate that information with this existing open source model in Sienna Ops to run a before and after case study, a base case without the renewable energy, and then a potential scenario including wind and solar. So this is a quick overview of what our next session will include. We'll quickly recap today's session before going over our workflow through the 3 tools again. We'll show resource visualization and site selection in the RE Data Explorer, and then move into SAM and Sienna to do the production cost modeling with our hypothetical wind and solar resources. And finally, we'll wrap up with a Q&A. If you are interested in following along with tomorrow's demonstration on your own computer, that's totally optional. But the case study code is available for you to download on GitHub at this PSI Cambodia link. An explanation of the demo is available in the README online, and it includes some of the installation instructions, which are also included here and can be also referenced from the link at the bottom. So we're going to be looking at 3 tools, but I do want to say that the resource data is already downloaded and available in the GitHub. So you don't necessarily need to go through the steps in the RE Data Explorer and SAM in order to model the time series data. It's already included in the GitHub. But for your reference, the access instructions are included here. The RE Data Explorer is just accessed online. No installation is necessary. The system advisor step is also optional because we have already processed the data and included it in the GitHub. But if you're interested in changing any parameters or doing a follow-up by adding additional wind and solar sites to the system, the 2 steps that we have used in the demonstration include downloading the SAM GUI and then also running SAM through the PySAM wrapper, which includes installing Python and setting the environment up as included in the GitHub README. So the main part of the demo is the production cost modeling steps in Sienna. And since Sienna is written in the Julia programming language, you would need to download and install Julia and then activate the environment again as described in the GitHub README. So with that, we'll wrap it up for today, and I'll pass it back to Holly for our Q&A.
Thanks, Kate, and thanks, Galen. I know a lot of people really appreciate you guys sharing these open data and tools, especially because they're applicable across such a wide variety of contexts. So there's certainly a lot of interest. Our first question is for Galen. And Kate, if you want to stop sharing your screen, we can just like look at the gallery. Galen, we have a question from Pramod, and it's how does the local pollution factor in while assessing solar resource potential for the solar data set? And then while you answer, can you also talk a little bit about the granularity of both the solar and the wind resource data set?
Yeah, great question. So an increasing concern for PV generation, especially in urban areas, is the impact from aerosols created by pollution. So, cities produce a lot of different types of aerosols. You have pollution from cars, from industry, surprising a lot from brake pads, cars moving around, those particulates move up into the air. So in our data set, we represent aerosols through satellite derived products. However, they're fairly coarse if you're really interested in understanding the fine scale impacts of that. So our data definitely captures the aerosols at urban scales, and thus will represent some of that impact on PV generation. But we've got some additional projects that we're working on to increase the resolution of how aerosols are represented, to look at kind of the benefits between PV production and also the impacts on air quality. So we've got some work in that space, but just do keep in mind that the solar data represents it, yet roughly pretty coarsely. And that's a really good segue to the second part of the question: what is the granularity? So the resolution of our solar data is based on the resolution of the geostationary satellites. So it depends on which extent in the world and also when. So the newer satellites have finer resolutions. So for example, the first 5 years of the Himawari data is 4 kilometer spatial resolution, and it's 30-minute temporal resolution. But the new satellite that the Japanese Meteorological Agency launched in 2015 and went live in 2016 is 2 kilometer spatial resolution and 10-minute temporal resolution. So we always produce the data set at the finest resolution of the satellite. So keep that in mind, and then we essentially map the aerosol data to that resolution. You'll notice in the Americas, we've got 2 kilometer 10-minute data. Across Africa, we've got a few years of 3 kilometer 15-minute data. So the data just continues to increase in resolution as new satellites go up. So always make sure you see what resolutions you're working with and keep that in mind for the application.
Thanks, Galen. Can you also tell me a little bit more about the other types of resources that are represented in RE Data Explorer? Is there geothermal? Is there hydropower, outside of the wind and solar resources?
Yeah, we do not currently have resource data beyond wind and solar. We are working on trying to create some data sets. Particularly, there's a lot of interest in hydroelectric, pump storage hydroelectric. So we will be developing some data sets that represent precipitation and thus the hydro resource in the future. Currently, we don't have any though. NREL does produce wave and tidal resource data that is available on the Marine Energy Atlas. That's currently a US-focused application, but there are plans to increase that into more of an international and global extent. But there are, and ready for some countries, there's some geothermal representation. So Mexico has some representation of the geothermal resource, but geothermal resource is a very different animal. And not something that NREL models. But when we do have access to the data, we do put it up on Ready.
Awesome, thank you. Our next question is coming from Billy, and it is for Kate. Do you see any opportunities of using PCM results to identify any critical system operating points that need further study in, say, dynamics or transient space?
Yeah, that's a great question. And the answer is yes. So this is where production cost modeling can be integrated as a preliminary step before running additional power flow models. So we can use a production cost model to identify key periods of stress in the system, like over the course of a year. That could include peak load time, as well as time when there are limited ramping resources available, or where we may be limited in terms of other types of constraints. And so we can then use maybe a selected hour where we think the system is particularly vulnerable in order to run additional power flow simulations, considering various contingencies during those stress times.
Awesome. Speaking of the PCM model, we have another question from Pramod about, is it possible to use this model to predict pricing for the power market, say for like a day ahead?
Yeah, that is one potential application for production cost modeling. So one of the outputs of a production cost model are the locational marginal prices. And of course, the quality of those price forecasts depends on the quality of your input forecasts. So, it could be useful if there's uncertainty in those forecasts to run a range of sensitivities with different potential range of where you think the weather and load forecasts are going to fall, to understand also the sensitivity and uncertainty in the prices.
Awesome. And then, kind of for both of you, a question from Derek, looking at, just energy transition plans or, equitable transitions. A lot of countries in Africa have just energy transition plans. And so, what opportunities do you see as being available for the engagement in these countries for renewable energy integration in terms of productive uses of energy for agriculture, for example, with a specific focus in like capacity building?
So that's a great question. In terms of the modeling tools that we're talking about today, I think open source models and data are one way of making information accessible to everyone. And that could include stakeholders that are doing local advocacy to verify that the decisions being made are in line with their needs. Another avenue that I think is currently under development is trying to understand how we would quantify equity metrics. And so in the production cost modeling, we were talking about this optimization of operating cost as the focus, but there's opportunities there to include various equity metrics in various stages of models, either as something that we measure as an outcome or as something that we include as something we're trying to either constrain or optimize. And so I think that's a developing area that I'm also not as experienced in, so we could follow up with other folks who are working more directly in that area.
Thanks, Kate. I would also just add, in terms of data and tools for Africa, we are developing a new long-term solar resource data set. Currently, there's only 3 years available of the NREL data. And so there will be a 16-year data set that will be released in about a year to 18 months from now. But we've done some work. The question touches on productive uses. And so these tools and data have been used in that context. So, email us and we can put you in touch with the person that was leading that work in Africa, but particularly there's some work done on the opportunities for PV for productive uses such as pumping for irrigation, agricultural purposes, fishing applications, using PV for refrigeration. And so there's definitely a lot of opportunities. We don't have the specific tools that model those explicitly, but the tools are broad enough for you to look at those opportunities using the data and simply SAM. You can look at what is the opportunity for a small scale PV system for a specific application. So the tools definitely enable that. You just have to kind of apply it to your specific case.
Yeah, that's a great point about, kind of the tools that are being developed. And if you are interested in learning more about these tools that are being developed for Africa specifically, you can reach out to the USAID-NREL Partnership, and Isabel will put the email for that partnership in the chat. A question from the Q&A: utilities typically purchase renewable energy data from multiple independent power producers, purchase renewable energy from multiple independent power producers. How is that taken into account for the PCM model?
That's a great question. So the way that we talked about PCM modeling today was focused sort of on market model. However, there are also vertically integrated utilities that have all of the information about what it costs to operate their plants already in hand. And in both of those models, I believe you might have power purchase agreements with a set price for buying wind or solar energy. So in that case, rather than you would want to include that as a specific constraint in the model. So the cost to operate that wind and solar system given by the PPA price can be used as input data to describe what the power purchase agreement includes. So that could be requiring the system operator to buy all of the available energy at that price, or it could include some option for the system operator to force curtailment on that plant if the electric grid requires that. And so those could be included as constraints in the model.
In that same vein, Kate, does the PCM model represent system reliability?
Another great question. So production cost modeling can be used to model the holding of ancillary services like reserves. So a system operator typically plans to meet the demand over the course of the next day, while also holding a bit of a margin because there's going to be unexpected changes and forecast errors. And so that margin is the reserve margin. A production cost model cannot model the deployment of those reserves. And so that's where we need to go to something like an AGC model and do additional load flow calculations in order to back up how the system would respond in the case of a disturbance. So it's the holding of the reserves, but not their deployment.
Gotcha. And then also kind of related, Galen, what are the limitations of the data from RE Data Explorer for PCM modeling or other types of grid modeling activities? You're muted.
Thanks. Great question. Yeah, so when we're using these data, it's important to take into consideration the resolution of the data and also the application of the use. So these data are, when you start looking at an individual site and you start looking at the individual the time series at very fine temporal scales, that's where the resolutions start to drop, the accuracy starts to drop a little. And so, for example, for project prospecting, that's where the data, you would definitely want to use that in correlation with measurement data if you're planning a wind plant. In the context of production cost modeling, I would say probably one of the key limitations, the most important limitations, is that the data set captures from a distributional perspective the ramping rates, but once you start looking at very fine temporal scales, the ramping rates really should be treated more as representative. And so generally in the model, the more you aggregate across sites, across a geographic extent, that's when you have more confidence in the data as it informs the model. So, I think just as a general approach, if you have a very few sites that you're representing from the resource data in the PCM, you're going to have less confidence than, in a larger system. So that's definitely something to take into account, is essentially you have kind of increased accuracy in the representation through geographic aggregation of the data within the PCM.
Yeah, absolutely. Also, like talking about the data that comes from RE Data Explorer, I know we talked a little bit about, things like air pollution, metrics like that, but what types of other metrics are included in that data? For example, like we have a question if it, factors in humidity, if it factors in other types of metrics. Can you talk a little bit to that?
Yeah, so both the wind and solar data include ancillary meteorological variables. The solar data provides a lot more variables, so it does include relative humidity. It includes albedo. Particularly if you're modeling like concentrating solar power, you need relative humidity, so we do include that. The wind data, typically, like the new data we're producing is just kind of the required variables for wind turbine modeling. So that includes temperature at heights above the surface and atmospheric pressure. But the new Southeast Asia data does not include additional variables. It's just kind of a computational limitation that we can't produce more. But we love to hear from users on what they need and what's not included. So I would definitely look, if you go into the RE Data Explorer and you go into the solar download, you will see the full list of variables that are included there, the ancillary meteorological variables.
Yeah, great. And then when talking about like granularity of data and how specific it has to be, we have a question about for optimization models to match demand and supply curves, you have to have the same granularity of data. How does one tackle a situation where you don't have granular demand data, but you do have granular supply data, or vice versa?
You want to take that one? I can.
Yeah, that's a really hard question. So one place to look for demand data is system operators often post historical data online at some level of aggregation. So that could be over the entire system, or it could be sort of a more zonal or regional area. And so that's a place to start is looking at the system operator website. But if you're entirely missing demand data, these models are only good as the input data. And so that is a really hard situation. Another possibility is that there might be snapshots. So if you don't have a full year, there might be some historical data available for only a few days, and you could use those as representative days. Another place to look would be in online algorithms that do various downscaling of time series data from, if you have a resolution that's 6 hours or something like that from a weather model, to do some temporal downscaling to hourly level if that's the resolution of the wind and solar resource. Another place to look would be to access historical weather data through something like the ECMWF, the European Center for Medium Range Weather Forecasts, that I believe has open sourced its historical weather forecasts, and then to try to do some sort of load modeling through, again, an algorithm that you might find in the research online to translate the weather data into a load profile. So those might be some options, but it is hard when there's just data scarcity.
Yeah, no data makes modeling difficult. We're nearing the end of our session, so we'll do one final question really quick, which is for future disruptions, for example, 5-ish years from now, how does the model get data for like future disruptions or extreme events? Or is there any model that can generate a set of scenarios of disruptions at different locations and days?
Want me to
Go for
start
it.
on it? So this is an exciting area of research. We're trying to understand what the future might bring in terms of resource extreme events and how that can be represented in a power system. So NREL has developed a modeling framework to downscale, so increase the spatial and temporal resolution of future climate scenarios. So we're looking usually a little bit farther out than 5 years. We're usually looking 10, 20, 30 years out into the future. So those data we're starting to produce, kind of stay tuned. In the next couple of years, we hope to start producing those data sets so that you could essentially do like everything that Kate was explaining, but you could use a future scenario of the wind and solar resource. Obviously, Kate, in the previous question, just touched on, demand. That's something that you would have to kind of forecast how you would think that demand profile would change into the future. But there are ways to do it. And then as far as extreme weather events, we've done some modeling there as well. And I think Sienna is very well prepared to do this as well, where you can look at historical extreme weather events to understand the impacts that will have. And then you're looking to the future again, once more of this downscaled future climate data is available, there'd be some opportunities to start looking at some of those questions. Obviously, it's a very uncertain space of modeling, but I think it's a really important question because we're probably just going to see more extreme weather events across the globe, and we need to understand the impact they'll have so that we can plan accordingly and develop the future power system to be more resilient to such events.
Yeah, absolutely. It's really exciting to be, on the forefront of these developments and see all these, tools and forecasting come out of this. Thank you both so much for your time today. We had a lot of questions and a lot of people found it really informative. We're looking forward to seeing you all tomorrow for session number 2. To find the resources for session number 2 tomorrow, you can visit the link on the Global Power System Transformation Consortium website, where it is optional, where you could follow along with Kate's demonstration tomorrow. Thank you very much, everyone, and we'll see you then.
Thank you all.
Thank you so much.